All right, in today's lesson, we're going to move on to a different type of function called the quadratic function. And the quadratic function is noted by the most basic one, y equals x squared, the mother function. So just like with what we did with the absolute value, let's make a table here and substitute in these x values and see what we get for the y values and draw a sketch. So negative 2 squared, negative 2 times negative 2 is 4. Because remember, x squared means that number times itself. Negative 1 squared is negative 1 times negative 1, which is positive 1. 0 squared is 0. 1 times 1 is 1. And 2 times 2 is 4. So this kind of resembles the mother function of the absolute value family because we see that all the y values are positive, except these y values went up faster than the absolute value function. So let's graph these. 4, there's one there. Dots. So you see it doesn't make a U shape like the absolute, or sorry, it doesn't make a V shape like the absolute value does. It makes more of a U shape because both sides go up quickly. It still has a vertex just like the absolute value ones. So it has a vertex at 0, 0. So vertex at 0, 0. The shape of this graph is called a parabola. So I want us to make the differentiation. This is a quadratic function. The shape of the graph is called the parabola. So if I say, hey, what type of function is this? Don't say it's a parabola. It is a quadratic function, and the graph of a quadratic function is called a parabola. Now the graph opens up. You see it goes up on both sides. This has something called the axis of symmetry. Axis of symmetry that we abbreviate AOS, and it's x equals 0. Now, the axis of symmetry goes through the vertex, and notice that the y values are on either side are the same distance away. Like this y value is 2 units away, and this same y value is 2 units away from the axis of symmetry. So we're actually going to use that today to help us plot some points to draw this parabola. Okay, and this is, again, the vertical line that passes through the vertex and divides the graph in half. The domain of every quadratic is negative infinity, comma infinity, no matter what. All quadratics have a negative infinity, comma infinity domain, and the range of this one is 0, comma infinity. Smallest y value, and it goes up. This one has a minimum value of y equals 0. That's the smallest y value. There are different forms of a quadratic function that we're going to study. We're going to start with vertex form because if you look here, it looks very similar to the general form of those absolute value ones. Remember, absolute value was y equals a times the absolute value of x minus h plus k. The a, h, and k do exactly the same thing they did for absolute value. They do the same thing for these quadratics. So our reflection in the x-axis, if a is negative, just like we had before, if a is negative. There's a vertical stretch if the absolute value of a is greater than 1. There's a vertical shrink if the absolute value is less than 1. Translation, left or right, h units, and up or down, k units. Same exact thing as our absolute value. And over here, vertex is still h comma k, so the opposite of what we see. Axis of symmetry is x equals h. That is a new one. but it will always match up with the vertex. And then you're going to have a min or max of y equals k, and that's new, but that will always match with the y coordinate of the vertex. So that vertex tells us a lot. So to graph, what we're going to do is we're going to identify and plot the vertex, which is h comma k. Sketch the axis symmetry, which is x equals h, which draws the vertical line, and then we're going to find a point. The easiest point to find is f of 0. That is the y-intercept. We substitute 0 in for x and simplify. That is your y-intercept. And then we're going to reflect that y-intercept over the axis symmetry, and then we're going to connect those three dots, forming a parabola, not a V shape. I know with 3 dots it's going to be very easy to want to draw a V, but we aren't doing that for this one. For quadratics, we need a U shape. Now, if the vertex is also the y-intercept, then we have to do a different point, f of -1 or +1. That will give us our 3 points. So let's graph g of x equals -2 times the absolute value of x minus 1 plus 4. So our first step is to plot the vertex. Our vertex is at +1 comma 4. Right here. Now the axis of symmetry is x equals 1. Now we don't know what if there will be a min or max at this point. When you could look at the graph, but we'll talk about that later. But let's do min or max after it's graphed. Y-intercept. So g of 0, -2 times 0 minus 1 squared plus 4. Okay, so we can use a calculator, but we should be able to do this without a calculator as well. So -2 times 0 minus 1 is -1 squared plus 4. -1 squared is +1. +1 times -2 is -2 plus 4 is 2. So our y-intercept is 0, 2. So we'll plot that right there. Now our axis of symmetry goes through the vertex. And it might be a better idea to graph that or draw that after you plot the vertex. Okay, so now we have our y-intercept. It is 1 unit away from the axis symmetry. We're going to go 1 more unit. That is our reflected point. And now we're going to draw a U through those points. So now we can do the rest of this. Our domain is -infinity, infinity. The range on this one, remember that's your y values going up and down. Well, the arrows are going downwards, so our smallest y value is -infinity, and the largest y value occurs right here at the vertex of 4. End behavior. Both arrows are going down, so as x approaches -infinity, y approaches -infinity, and as x approaches +infinity, y also approaches negative infinity. And now min or maximum. This has a maximum because it has a top, and it's y equals 4. Now I want you to notice something. Our k value is 4. Our range had a 4 in it. Doesn't necessarily need to be the biggest number, but our range should have a 4 in it. The vertex has a 4 in it, and the min or max also has a 4 in it. So that k value will tell us those characteristics. Right, if we flip the page here, we're going to graph this one now. So our vertex is at -2, -3. -2, -3, right here. So that is also where our axis of symmetry will go through. Now we're going to find our y-intercept. So h of 0 equals 1/2 times 0 plus 2 squared minus 3. Alright, so we simplify this. Uh, 1/2 times 2 squared plus 3. 2 squared is 4 times 1/2 is 2. Minus 3. Minus 3 gives us negative 1. So our y-intercept is 0, negative 1. There. So then we reflect that over the axis of symmetry. So 2 units away from the axis of symmetry. We're going to go 2 units more. 1, 2. And then make a nice U shape. So that was what our graph looks like. Now all this other information here, it comes from having that vertex and graph. Axis of symmetry is x equals negative 2. Domain is always negative infinity, infinity. Our range, this one's opened upward, so the smallest y value is negative 3, and we're going up to positive infinity. End behavior, both sides are going up, so as x approaches negative infinity, y approaches positive infinity, and as x approaches positive infinity, y approaches positive infinity as well. Because this has a bottom, this has a minimum value. So that is at y equals negative 3. In comparison, that is your RST, remember, so R, there is no reflection over the x-axis. We have a vertical shrink because 1/2 is smaller than 1. And our translation, we are left 2 and down 3. So the exact same process as we did for the absolute value functions. All right, now this one here, we have 2x squared plus 1. The first thing you'll notice is that there's no parenthesis. Okay, well, if there's no parenthesis, that means your h value is 0, because we wouldn't want to write it. It doesn't make a whole lot of sense to write it like this. F of x equals 2 times x minus 0 squared plus 1. But if that helps you to identify that our vertex is 0, 1, you can do that, 0, 1. Now, like I was saying, like we said up here, if the vertex is the y-intercept, and this one is, our y-intercept is 0, 1, we need to find a different point. So let's find f of 1, and then we'll reflect that. So f of 1, 2 times 1 squared plus 1. 1 squared is 1, times 2 is 2, plus 1 is 3. So that means 1, 3 is a point on this function. Our axis of symmetry goes through the vertex. We are 1 unit away from the axis of symmetry, so 1 unit on the other side. And then we're going to draw our parabola. And again, you want to make sure that these do not look like absolute value graphs, so they should curve upwards. Okay. So now we have the y-intercept ready. We already graphed this. So our axis symmetry is x equals 0, the x coordinate of our vertex. So x equals 0. Domain, always negative infinity, infinity. And then our range, well, it's open upwards, so it's the y-coordinate of the vertex, comma, positive infinity. And end behavior, both ends are going up. So as x approaches negative infinity, y approaches positive infinity, and as x approaches positive infinity, y approaches positive infinity as well. All right, so graphing them is not that difficult. You just have to remember the process of getting that y-intercept and reflecting it over the axis of symmetry. That's the monkey wrench in this. Now, let's look at these where we're going to identify this information without graphing. So the vertex in this one, g of x equals 2 over 5 times x minus 6 squared plus 4. Vertex will be 6, comma 4, which makes your axis of symmetry x equals 6. Because your a is positive, our graph opens upwards. Look at all of our opening up graphs. A is positive. A is positive. This one, a is negative 2, and see we're open downward. So because it opened up, this is opening upwards, we have a minimum at y equals 4. Domain is always negative infinity, comma infinity. And then the range. The range, because we are opened upwards, is going to be 4, comma, positive infinity. All right, this one over here, our a is a negative 1, but our vertex will be the opposite of that, so negative 2, comma 1. Axis symmetry is x equals negative 2. Because we are having a negative a value, this graph will open downwards, giving it a maximum at y equals 1. End behavior. Because the graph goes down on both sides, we say as x approaches negative infinity, y approaches negative infinity, and as x approaches positive infinity, y approaches negative infinity as well. And then comparing in words, that is RST. We do have a reflection over the x-axis. Shrink or stretch, because a is 1, negative 1, there is no shrink or stretch. And then translation, we are left 2 and up 1. All right, now that we've done this, and look at, we were able to get all this information without even drawing a graph. Yes, I drew this sketch up here just to show you that since a is negative, we know what that looks like. But if you understand, oh, if a is negative, it looks like that without having to sketch it, then you don't even need to do that rough sketch. All right, last one. Write a quadratic in vertex form. So what we've been doing in quadrant 2, where it has a vertical shrink and an end behavior like that. Because both sides are going down, that means a is negative. Okay, if a is negative and it has a vertical shrink, I can do something like negative 1/2. Now, if my vertex is in quadrant 2, the h value needs to be positive, because it's the opposite of what you see. And then the y value needs to be positive because it's exactly what we see for that. So this function has an end behavior that goes down on both sides, a vertical shrink, and a vertex in quadrant 2, because the vertex of this is negative 4, comma, positive 7. Okay. So that's graphing in vertex form of a quadratic. A lot of similarities to those absolute value graphs. So hopefully there wasn't too much that was new here, just that y-intercept piece that was new. So thanks for watching. Make sure to like the video and subscribe.